So we have an air turbine that's operating at steady state. We're given some inlet conditions and some outlet conditions, and we are told that the velocity at the inlet is much less than the velocity at the outlet, and that the velocity at the outlet is 90 meters per second. We're asked to find the mass flow rate and the area at the outlet, and we're told explicitly do not ignore the kinetic energy changes. So let's go ahead and get started. So the first thing I'm going to do is I'm going to apply my conservation of mass, see what that gets me. So if it's operating at steady state, m.1 and m.2 are equal to one another, and you could just call that m dot. That doesn't get me too far, but I'm going to go ahead and apply my conservation of energy. So I could at this point, I could have applied, could have used the equation for mass flow rate. So it's the area times the velocity divided by the specific volume. But I'm missing some information. So I don't know the velocity at the inlet. In fact, I'm told it's negligible. And I don't know the area at the inlet. And of course, at the outlet, I'm missing the area at the outlet. I got to figure that out. So I'm going to apply my first law. And I'm going to get rid of some things. So dE dt goes away because this is steady state. And normally for a turbine, we don't worry about the kinetic energy changes, but this particular problem gave us some information to consider, so we're going to consider it. Now, because the problem said that the inlet velocity is small compared to the exit, we're going to also say that the kinetic energy at the inlet is negligible compared to the outlet kinetic energy, because if V1 is much smaller than V2, then V2 squared is going to be or if V1 is much less than V2, then V1 squared is going to be much, much less than V2 squared. So I'm approximated that V1 squared over 2, I'm approximating that as 0. And then I just need to solve for m dot and then plug in my numbers and pay attention to my units. And if I do that, I end up getting 4.59 kilograms per second. So let's see what else we've got. Now we need our area at state 2. So here's where I'm going to, and you can assume 1D flow here. So you've got the area, the velocity, and the specific volume. Sorry, that's my daughter in the background. But I've already solved for the mass flow rate. I need the area, so I just kind of rearrange things. Oh, and I use my ideal gas law to define the specific volume. I rearrange things to get the area at state 2, and then I'm just plugging in some numbers, paying attention to my units, and I end up getting 0.066 meters squared. All right, well, I hope that was helpful. Thank you for watching.